All right. Okay, I guess let's get started. Yeah, so as I said, I think I will postpone homework one because it you probably need to use some property of the entropy, which I tried to get to last week, but I couldn't. Uh, so yeah, and then the next homework I'll probably post sometime between Thursday and next week. Uh, but yeah, so last week we had 3 classes, and I tried to rush a bit too much and I think made many mistakes. So I apologize for that. Uh, yeah, I think we can slow down a bit because there's a quantum computing next semester too. So if we miss something and we want to see it, we can shove it to the to the next semester. All right. So last time we talked about uh, uh, justification for the probability law from the subjective probability point of view. Probability. And if you remember, is so there are probably many ways to do it, right? But the I guess now canonical way done by Definity was to consider some kind of wager or betting and trying to assign a fair price to some monetary value that depends on chance. And last time, so I sort of almost got to the last of the axiom, but then yeah, I didn't really like sufficiently explain it enough to get to actually the axioms, which I will do that now. So this is the product rule, and the difficulty is that this involves conditional probability, right? And then I introduced a lottery ticket like this that we will assign a price if A and B, or let's see, the conditional you get paid. You can, well, so since we want to get the conditional probability, right, which would make sense, this event would make sense only if B is already true. And so to prevent a sure loss, I have to have another disjoint condition that says that if B is false, then I get a refund. So if B is false, I'm fine. I don't lose any money. And then if B is true, the first condition reduces to, A is true, given that B is true. And so if I assign a price Q here to this ticket, to prevent a loss, I should assign this value to the ticket. Right. But how to get this law? Well, the extra step that I missed last week is that, okay, we just do it in the sense that these two events are disjoint, and so I can actually try to split this into two tickets and then apply the other axioms, the sum rule, and see if I can get this law. So this ticket, and then so I would assign the R dollar to this ticket and S dollar to this ticket. Well, this from what we previously discussed, this R should just be the joint probability, right? And then the S. So if the value of this, well, if this amount of money is just 1, then it would just be the probability of that B is not true, right? But then there's nothing special about this value 1. The value, the subjective value that that we assign to each ticket is really just a prefactor, a multiplication ratio that we use to if this is worth, like, if you can cash in for $M, then this would just change to like R times M. And so the value of this that we assign should be this. And so from the third axiom, since these two are disjoint, and then the union of these two events is just this one, right? And so it must be true that this is the case. And so let's plug in the value. Then, as you would prove in your homework from other axioms, this is just 1 minus the probability of B happening, right? And so for the two sides of the this cancel from the two sides of the equation, and I have minus sign here. So if I move it to here, then we get what we were trying to prove. Any question about this or any stuff last week? All right, so last week I also showed pretty quickly, and we'll come back in more details again, but just I just note here that so suppose that I have a sequence of some variable that can take some value in a set of size D. So length n sequence where each random variable, so you have like a random source of bit or dit, right? This has if this has D value, then this is dit. So I say that all of them are, so they are this is like an IID sequence. So, all xk distributed according to some random variable x, which takes value xj with probability pj, and then J is goes from 1 to D. So this is like throwing a 6-sided die n times. Then I say that let's say that a sequence is typical if the number of occurrence of symbol A of some symbol xj. So I call the number nj of xj is the total numbers times the probability. So of course this can only be the case in the large n limit, right? Because nj has to be an integer, but usually n times pj is not an integer. But then so then I show that the probability of finding any typical sequence is last time I used log base 2. It's this. And then further I show that the number of typical sequences which is just a multinomial coefficient, right? This big N factorial divided by like N1 factorial times N2 factorials and so on. And then I used the Stirling approximation. Which usually I just use log the natural logarithm base e, and this would this is kind of like the entropy, right? But you just change the base to the natural to the base e. But then if so, we can actually just for convenience, I can just go ahead and change the base. So now if I take the log of this quantity, base 2, right? Base 2, and then just plug in that equation, I get the natural log of this guy, which just brings the whole thing down. And then I can distribute log 2 to every one of them, right? And so this turned into log base 2 here. And so there's already minus sign, so this is yes, log of the number of typical sequence is n times the entropy of the source of the variable. And so I mentioned something about data compression. So to be more explicit, so what is the probability that we get from typical sequences? The probability of all typical sequence. So it's just the probability of each sequence times the number, right? So the number here is just 2 to this power. Sorry. This is 1. So in the large n, when n goes to infinity, the typical sequence takes all the probability. Okay, that is a word. And so you can imagine a strategy of transmitting these value of random variables, so like encoding it into some symbol, and then send the symbol. Right. So intuitively, sequences with low probabilities, you well, if you consider lossy data compression, so you just try to throw away sequences with low probability and hope that you never have to send it. If you have to send it, then it's an error, right? But from this statement, you can imagine that when n is large, you can try to only assign a symbol only for sequences in the typical set, like these typical sequences, and there are this number of them, and all of them have the same probability. And so this is, but to do so, you have to encode not just each. You have to give symbol not just to each bit in a sequence, but you have to take into account all the n symbols here. So this strategy is called block coding, which is just to encode n symbols at the same time, and then you have to determine the number of n when you can say that n is large, so you can ignore all of the sequences that are not typical. But we will come back to this later to make this more precise, because yeah, we know like when we talk about the law of large number, right? So in reality, n is never infinity, so we have to take into account some kind of error, right? But yeah, so yeah, this entropy thing kind of appear in many places. So I like to discuss some basic property of this function first. So Shannon entropy. So if I have a source of a symbol with the alternative, but then okay, so I'm gonna be kind of abuse the notation a little bit, and then I just say this little x in the set capital X, and by which I mean this can take one of the d values here, okay? And log base 2 of this. Sometimes we would also say that this is the expectation value of these random variables, the surprisal. This is the amount of information or the degree of surprise that you have when you see a symbol. So yeah, the right. So this is log 1 over p, and so when p is small, this is large. So you're more surprised when you see a rare event happening. So we'll talk about some general properties, but let's look at the simplest case first, I think. So the binary entropy is when you only have two alternatives. So when these two, so I will just denote it as H2. This function is just log x minus 1 minus x log of 1 minus x. So what does this look like? One this looks like this, like a bell. So it takes the minimum value when x is 0 or 1. So when the random variable is just deterministic, and it has the largest, it attain the largest value when the both alternatives are equally likely. Right, so we have a name for this type of functions that's kind of like an inverted bell, like this, because concave function. Because well, it is concave because it has some kind of concavity property. So, but first, so what is this thing? Well, intuitively, it just means that if I say take any 2 points and then draw a line between them, this is under the curve. So to be more precisely, I have to define something called convex combination of points. So let's see if I want to use symbol x and y. So this is basically just a special kind of linear combinations, is like a probabilistic version of linear combinations, where if I have a convex combination of x and y, this lambda must be positive and less than or equal to 1. And then you can imagine this geometrically, right, as drawing a line between 2 points. So if I have, let's see, x, y, then, well, what is this guy? So just y, okay, y, and then I want y minus x or x minus y. Okay. And this, which is this line, if I think of it as a vector, right? And so lambda just parameterizes our points on the line joining the point x and y. And you can use this to also define something called a convex set. we should be, well, geometrically is a set in which if I pick any 2 points and draw a line between them, it never go outside the set. So mathematically, this would just say that for any pair of points, all the convex combinations. So let me just to prevent confusion. So this is a spatial type of linear combination. Then these points are also elements of the same set. So it's called convex set. For here, when applied to a function, okay, I just have to just make the sign right. So if I have so we are basically we are comparing taking a function of a convex combination or taking the convex combination of the values of functions. And it is this direction, it says concave. The other is convex. So here, if I want to apply this new terminology to the graph again, so the left-hand side would just mean that let's say I take these 2 points. The left-hand side would be I take the value of this function and then form a convex combination of them. Whereas on, sorry, that was the right-hand side. Right-hand side. And so but for the left-hand side, I take the convex combination first of the input variable of the graph, and then take the value. So for example, if I take the value in the middle, this would be the left hand side would be this point. Right? Yeah, and so being concave function means that the graph is well above any lines that you can draw to join 2 points on the graph. So so let's see, or maybe, well, I don't know, I haven't counted how many properties I would list. Let's say one thing is concavity. So what does this mean physically, right? Or may not be physically, but statistically. For the entropy function, so it turns out this is true for any h, not just the binary entropy. But let's say okay, absolutely, but I just want to okay, since it's true, then I think we just ignore this. So being concave, right, means that if I have a convex combination with probability p for, oh god, maybe I want lambda because there will be too many p's. Okay, so let's say there are 2 binary distributions, so PA and 1 minus PA and PB 1 minus PB. So you can basically, for example, imagine this as like a two type of coins. Yeah, maybe this is like Thai baht and some kind of American Australian dollar or something. And well, in the first situation, so suppose that I toss this coin with probability Q, and this with probability 1 minus Q. So that means now my uncertainty is not only whether the coin will come up head or tail, right? It's also which of the coins that I have. And so the random variables here that I will the variable here that I will put as the base probability here would just be this. So this would be like the probability that the head comes up. Right? When it the concavity says that this is this, right? Which means that by tossing the coin, I would get more information. Then, so let's see how to say it. Yeah. So if here would be like either if I have two separate coins, right? And the HP and HPB would be the amount of information that I learn by just tossing one kind of the coin. But then if I toss the coin without knowing whether it's the coin A or coin B, I would actually get more information because beyond learning that the outcome is head or tail, I could also in theory learn the identity of the coin. So for example, if for coin B, if coin B is like very rare for the head to come up, and then if I toss a coin and then I get hit, then it's more likely that I have the other coin. Is that okay? Any question?
What if I put with that, right?
Yeah.
And after that we do what?
Yeah. So not sure what the question is, but this is just maybe I can say it this way. Maybe this is just comparing the amount of information that you would get if your random variable is this, which means that I have two coins and I don't know which one it is, and then compare to sort of like the convex combination of the information that I would get if I just have one of that type of coins. Yeah. So yeah. So I think yeah, of course that is a great question. So H is the channel entropy is typically
of who
so you mean the spatial example? Yeah. So if the coin B is very hard for it to be the it's very rare for a head to comes up, and then the head does come up, then maybe it's more likely that uh, we have coin A instead.
and then you say the more.
Yeah, so this is left hand side. That is the Shannon entropy is greater than
Or it's like more information if you know.
yeah, that's why the question what is information is great, because people call the Shannon entropy both information and uncertainty. Because they think about different points in time. So if I have like a random source, right, which I don't know, it's just like has the potential to spit out like some symbols. So over here, people tend to think of the Shannon entropy as a measure of uncertainty. Well, of course, the why is measure uncertainty has to be justified. It doesn't have to be Shannon entropy. This is just like some spatial choice of function. But then if I look at it and then I learn that, well, in this specific instance, for example, the value x occurs, then this is the amount of, well, over here people would associate hx with the amount of information we can learn from the random source. Or maybe thinking in like the extreme case, if there's no uncertainty, so the random variable is just a trivial one, just deterministic, both of these would be zero. And also, yeah, the Shannon entropy would also be zero. So because it's if if there is no like if the situation is deterministic, then you would already know what to expect before looking at what the value of the variables. It's something like if your mom call you, but you already know that your mom what she will say every time she call you, and then she call you anyway, and then but you're like, okay, you just said the same thing. You don't really learn anything new. Right. Yeah, so I guess intuitively that would be, be if I say because before we learn the value we had maximum uncertainty, would that just be circular? But it's kind of like that, yeah. Yeah. But of course, this is just like yeah, I just use words, right? Like uncertainty and information. And as I mentioned, there are other functions other than Shannon entropy that you can use. But this has a special properties because it's additive when x and y are uncorrelated. So let's see. Well, we haven't, I haven't defined this yet, but let's just say. Well, it has other property as well. Okay, I think yeah, I can mention that now. This is one of the property, but it's not something that pick out Shannon entropy. And you can treat this as just like little fun facts. So the way I put it in my note here is probably from Kinshin. So he would say something that we would call entropy or information measure would have this property. The first is the function is invariant under permutation of the label x. In other words, the only thing that matters is the distribution itself, right? It doesn't matter if px is really attached to the symbol x or other symbols. And two, x is maximum when all outcomes are equally likely. The third one is that adding events or adding alternative with zero probability doesn't change the value of the function. The p, and by here I just mean this, right? It's like p1, p2, pd with zero doesn't change x, doesn't change h. And then a special one, which I guess we have time to talk about later today. Yes. Is this direction correct? Right. So I haven't really introduced this, but it's sort of the symbol kind of suggests what it means. Right? So this is saying that all the information, if I have two random variables and I look at both of them jointly, the information is this joint Shannon entropy is the same as the information. So learning both x and y would be the same as learning x, and then learning why, given that we know uh, the information about X. And this is true for Shannon, but not true for other entropies like Renyi entropies. Do you remember where's the accent in here? Is it here? Is it here? Oh god. Yeah, I wouldn't have that one. Okay. Yeah, which are also measure of randomness in some sense. It's a yeah generalization of Shannon entropy. It's sometimes easier to compute, but what I've heard is that what I've heard is that you cannot really build so the information theory that's about like data compression and stuff that's built out of Shannon entropy. You cannot really do that with other kind of entropy. It's like it has some something special that makes it the most useful. And of course, if you want to learn about even more generalized entropy, you can ask Ajahn Rin. Yeah. And for example, for those who know the purity, the log of the this tends to be a negative log. Yeah, the negative log uh, of the purity is also one kind of Renyi entropy. Okay. What else should I say? Okay, so from now on, I think it will be I just list and prove some of the properties of entropy, of Shannon entropy. Yeah. Or related or related like uh, function like the joy entropy and the conditional entropy. But first, for the concave or convex function, there's something called Jensen inequality. Which is a statement about the expectation value of function, whether it's concave or convex. So this is just defined to be Px of fx, right? Oh no, it's probably opposite, right? Let's see. Wait, just let me check to make sure. If it's a convex function, then the expectation value is greater than, no. Right, because it should follow directly from the definition, right? Because the left hand side over here is the right hand side here. Okay, so now let's see if I can prove the following statement with the sign switch around. There's also another quantity that often appear called relative entropy or KL divergence. It's Kullback, Lieber, divergence, and it is a way to compare two probability distributions. Maybe there's not enough space here. So say if I compare P and Q, and I define this to be x log px over qx. And let me check the sign again. Maybe this is different. The Wikipedia said this is plus. But we'll see, because this has to be positive, and so we can use Jensen inequality here and see if this has to be plus or minus. Yeah, so it's a comparison between two probability distributions. So sometimes it's especially like machine learning is usually used to try to quantify how far two probability distributions are, except that, and people say it's kind of like measuring distance, except that it's not a distance measure because it's not symmetric. Not a true distance. But it's also a quantity that comes up as an intermediate step when you try to like compute things. So the very, for example, I will try to show this first, that the relative entropy has to be positive. And then use that to show that the Shannon entropy is at most log D. It's just the log of the number of alternative. Okay. Yeah. I don't need this. Okay, let's use Wikipedia definition and then see what happens. So I think there are many ways to prove this, also without using Jensen's equality. But if I use the Jensen's inequality, uh, yeah, by the way, this is also this. Right? Okay, nice. This agree with the Wikipedia definition. Let's see. Minus, where should I put minus? Okay. So this is an expectation value of this function. Right? So this is one way using Jensen's equality, but you are sort of already have to know that this function is maybe this either convex or concave. So let's see. This is the expectation value. Okay, this is where it's a bit weird to me. I can check again after the class, but if you can use Jensen's, and it turns out that this is the direction of the inequality that you would use right, to claim that this is greater than 0, and then this is sum of probability, so it's just 1. And now, okay, so if we accept this as a fact, then we would have this inequality, right? So suppose special case that qx is 1 over d. So if the random variable q is equiprobable, then this would just be plus log d, right? And then this guy goes away, and then if I move minus the entropy here, I get that it's upper bound by log d. So here somehow use concavity or convexity. anyway, I believe that you have to use something like this. In the last problem. Yeah, so now let me introduce entropies when we have more than one random variable. Any questions? Which one? Okay. Click on it. So first of all, of course, if I have two random variables, then I have the joint entropy. Where it's the same as just the usual Shannon entropy, right? But then I just use the joint probability distribution. So to define a conditional entropy, so first, say if I want to think about probability of X conditioned on Y, let's say for Y fixed, I can define define this kind of entropy using the conditional probability, right? Because conditional probability when Y is fixed is a true probability distribution. This is, and then the conditional entropy is defined as the average of this over all Y. Yeah. So then we can show the identity that we allude to earlier. That is, this is just the joint entropy, and then you subtract the entropy of the variable that you condition on. Okay, so how to show this? So you just write it out, right? This is a sum now of X and Y. Then you got Py, X condition on Y. Then I have to have minus side too. Okay, important. Okay, now this combined into the joint probabilities. Yeah. And then I can split this log into log of joint probability and then minus, which turns into plus of y, right? Yep. For the first term, we already have the joint entropy, right? And then for the second term, I have sum over y and then sum over x. I write this way, and then log of py. What is this? This is just the marginal, right? And therefore, this whole thing is the negative of the Shannon entropy. So the joint entropy itself, so does it tell us about the correlation between two variables? So if x doesn't depend on y, so if there's no correlation, then it would just say that the joint entropy is just the sum of the entropy of two parts, right? Another quantity that people define to talk about correlation is also important in Shannon's theory is the mutual information. This is mutual information between x and y. Some people use colon like this, some people use semicolon. And then it's just defined to be this kind of comparison. Right, so this argumenting in the log sort of directly measure how correlated x and y are. And I will just write it here that so is the information that you gain from learning x and learning y separately, and then or saying it another way is like the information that you gain from learning x and y jointly that are not in like separately in x or y. Oh, there's a different way to write it, right? Or since it's symmetric, you can also write like this too. Yeah, there's a bit of a difference in size between like this and that. And actually, there's a really nice way to um, remember or work out the algebraic relation between all these kind of entropies by drawing Venn diagram. Maybe I want more space. And say these are the entropy of X and Y. Right. And then this whole thing is the joint entropy. And so the part of X and Y that is not overlapping with the other should correspond to the conditional entropy, which we can see here. So if I subtract from the joint entropy of Y, I get entropy of X given Y, condition on Y, and the other thing is also. And the the mutual information would just be this area. Right, because it's the area of X plus the area of Y, and then you so it will be greater than the joint entropy by this amount that's overlapping. Can we generalize this to more than two random variables? Well, you can find out in the third homework problems. But when you try to do something like this with the Venn diagram, then you get some kind of entropy of three variables, but it turns out it can be negative. So that suggests that this way doesn't work for three or more variables. However, when you go to quantum mechanics, you also see negative entropy. And you can either think that it's wrong or try to find the meaning of negative entropy there. Then, of course, the usual the convention is that entropy can be negative, the way that people define in quantum mechanics, and that it has some meaning related to entanglement. Okay. So I think at this point, all the homework can be done. The last problem is a bit long, and actually I haven't written the solutions myself. There may be many ways to do it. But it's about interpreting Shannon entropy as sort of like the number of yes/no questions that you have to ask in order to identify the alternative that occurs. For example, do you know how? So when we go onto the internet, sometimes we want anonymity, right? That we don't want people to know who we are. But do you know how many bits of information you have to gain in order to identify exactly who you are? So I calculate this with Wolfram Alpha beforehand. So this day, I believe, if you Google, they say that the Earth has the population of the Earth is about 8 billion, so it's 8,000 million. And then if you take a log of that, it's a bit less than 33 bits. So yeah, if you you just your privacy is only worth 33 bits.
You mean if we have some that we can divide it.
Yeah, so right. For example, and sometimes or intuitively you can sort of, if you measure in terms of bits and not bits or nets for natural log, then you can sort of think of bits as the number of yes no question that you have to ask. For example, if someone know whether you are male or female biologically, then that cuts about half of the population. And if you can find a question like this, then each question will cut, each binary question will cut half of the population away. And after about 33 questions, they will know who you are. Yeah, so therefore something like this, there are some criticism of like the manga Death Note on the internet, because Light revealed too much information about himself, being in Japan and being a student and something like that. So actually what Light somebody say what Light should do is that he should spread misinformation. Yeah, if he were smarter. So in the last problem of the homework, you formalize this sort of notion of Shannon entropy as the number of binary questions that you have to ask to identify the alternative. Because of course the complication is that usually probability is not a power of 2, right? It's not like a negative power of 2. So sometimes you have to do something more complicated than just ask binary question. Well, you can still ask binary question, but you will not cut out exactly half of the alternative. Yeah. Okay. If there's no question in the last 10 minutes, I would like to start the putting the rigor on the idea of lossy data compression. Oh, and actually, I listed out some like properties of. There are more properties of Shannon entropy, but there are too many, and it's sort of kind of hard to organize. If you want to look at, it's on page 506 of Nielsen and Chuang. Yeah, this is what we are talking about. Is like chapter 11, almost the end of the book. Okay, right. So we had shown previously that for a typical sequence, so now we are back to the situation where we roll d-sided die n times, right? And then try to look at length sequence of symbols. And consider a typical sequence which we define that the number of occurrence is exactly the expectation value. So this is that is the long run frequency of the number of events happening is exactly the expectation value. We had shown previously, so I would denote the probability of getting some sequence like this. So sorry, it's n, yeah. And then we show that this is 2 to the minus n times the entropy. But now I want to allow some error when n is not infinite. So we define not just a typical sequence, but an epsilon typical sequence. To be a sequence whose empirical entropy, empirical surprisal is close to the Shannon entropy. Yeah. In other words, after some straightforward manipulation, we are generalizing that kind of statement to an inequality. And so the goal would be to get to something called the asymptotic equipartition property, which basically is the generalization of the statement that we say earlier that for a large n, the typical, okay, so just to make it easier to say, I would say that a set that contains all of the typical sequence, I would call it a typical set, or here epsilon typical set. And I will denote by the script t, and it has a parameter of n and epsilon. So we want to get some statement of the kind that this typical set will, for large n, which we have to specify now, depending as a function of epsilon and other things, that for large n, we want to show that this set basically take almost all the probability on the space of sequence, and also each sequence in the set would almost all like equiprobable. And further, and that would give us a strategy to do a block coding, right? We would know based on like epsilon and other parameters what is the value of n that we have to go to, or for the error to be negligible, in the sense that the non-typical sequence that we throw away would have a negligible probability. That is, that we can suppress the probability of atypical sequence to be as close to zero as we want. And then we also want to show that there is no smaller set that does the same job as a typical set. In particular, we can show that if I have a set that is significantly smaller than the typical set, then we can always suppress the probability of that set to close to zero. So it will never really matter. All right, so we'll do that on Thursday. Thanks for coming to class today. Bit late.